Adventures with Calculus by Susan Shaw and Amanda Weber.
Once upon a time, in the magical world of mathematics, there lived a young student of calculus. Now, at that time, the land of mathematics was a dark and sad place. An evil sorcerer had recently stolen the Book of Larsen, the magical text that was responsible for all the calculus in the world. The algebra and geometry scholars thought little of it, but the young calculus student knew better. Without calculus, the world would become linear and flat. So he pledged to bring back the math he studied, and he went on an epic quest. The first leg of the student's journey was over the great rolling hills. When the student reached the hills with his trusty wagon, he soon realized that the hills would soon become flat. Without calculus, they could have no derivative, no tangent line, and no slope at a given point. So to ensure that the hills remained hills, he decided to solve a simple calculus problem to find their slope at a given point. The student needed to find the slope at the bottom of the hill, where the slope is the largest, to see if he could bring his wagon. The student knew that his wagon could be pulled up on slopes that were between -8 and 8. To determine if he could bring his wagon up the hill, the student decided to solve a simple derivative problem. First, he found the formula of the hill to be y equals -1/4 x squared plus 6. Then he graphed the hill and found the derivative to be -1/2 x. After graphing, he also knew that the base of the hill would be at x equals -5 and 5. So he plugged those two x values into the derivative, where he found the slope to be 5/2 and -5/2, both of which were between -8 and 8. With that, the student pulled his wagon over the hill and distributed calculus as he went. And so the calculus returned to the hills, but it was not enough. The student's kingdom was still in danger of becoming linear.
Next, the student reached the harbor. He chartered a ship to cross the sea. But halfway through their journey, the waves became too mild, and the ship was no longer carried forth. To restore the calculus to the sea and bring back the waves, the student decided to use an integral to find the area of the perfect wave. The student decided that the formula of the curve of a perfect wave should be f of x equals 1/2 sine of x. That way, the wave would not be too wild, but would help the ship through the water. To find the area and bring back the perfect waves, the student decided to find the area of the function from 0 to pi, where the function was positive. He knew the formula to find an area on a given interval was area equals the integral of a to b f of x dx. So he plugged the values he knew into the standard equation and got the area is equal to the integral from 0 to pi 1/2 sine x dx. And since he knew that the rules in the Book of Larsen said that you can pull a multiplier to the front of the equation, he simplified the equation to 1/2 times the integral of 0 to pi sine x dx and solved for the problem. And by looking at his work in which he plugged in the values of negative cosine x, which is the integral of sine x, and multiplied by 1/2, he got a value of 1. The student found the area of the perfect wave to be 1 meter squared, and the waves returned to carry the ship along. And so calculus returned to the sea, but it was not enough.
That night, the student reached a fortress-like castle. Pi was imprisoned there, and he needed to free his valuable friend because he had heard of a terrible dragon guarding the evil sorcerer's lair, and he knew that it was very likely he would need to solve a volume problem. But when he reached the doors of the castle, the citizens would not let him in. So the young student set a ladder against the wall of the castle and climbed all the way to the top. Just as he was about to climb over the wall, a guard saw the ladder and started pulling it out away from the wall. Curious, the student decided to use a related rates problem to evaluate the rate the ladder slid down the wall and the area, and to bring calculus back to the castle. The math student knew that the ladder was 13 feet in length. He also knew that when the base was 12 feet from the wall, it was moving from the wall at a rate dx dt of 5 feet per second, and that x is the distance between the base of the wall and the base of the ladder, and y is the distance from the ground to the top of the ladder. The question the student wanted to answer was, how fast is the top of the ladder sliding down the wall when x equals 12? In other words, he wanted to find dy dt at that point. To solve it, he used his related rates knowledge. First, he implicitly differentiated the Pythagorean theorem. The implicitly differentiated equation he found was 2x dx dt plus 2y dy dt equals 0. To find dy dt, he isolated it, which left him with -x over y times dx dt. He plugged in what he knew to solve for y in the Pythagorean theorem and got that y equals 5. With all the information he knew, he put everything into the dy dt equation and got -12. Since it was a negative value, it indicated that the ladder was sliding down the wall. His final answer was that the ladder slid down the wall at a rate of 12 feet per second.
The student looked at the ladder. He was also curious how the area of the triangle formed by the castle wall, the ladder, and the ground was changing. In this problem, he knew that he needed to find the change in area over change in time, or dA over dt. He knew that the area equation was 1/2 times x times y. To find the dA over dt, he implicitly differentiated the equation using the product rule and got dA over dt is equal to x times dy over dt plus y times dx over dt, all multiplied by 1/2. He knew that at the time x equals 12, dy over dt was 5. And from the last problem, he gained the knowledge that at y equals 5, dx over dt was -12. He then substituted all these variables into the dA over dt equation, where he got dA over dt is equal to 1/2 multiplied by 12 times -12 plus 5 times 5, which simplified into -59.5. With that, the student knew that the area of the triangle was decreasing at a rate of -59.5 cubic feet per second. So after the young student solved the problem, he jumped safely to the ground, and the guard was so impressed by his calculus knowledge that he let the student stay at the castle for the night, and he freed Pi to aid the student. And so calculus returned to the great castle, but it was not enough. After days of travel, the student and Pi finally reached the lair of the dragon that stopped any intruders who sought the evil sorcerer. The dragon perched on top of piles and piles of treasure, but much to the adventurer's surprise, the dragon was distraught. Its piles of treasure were soon to diminish without calculus, becoming linear instead of curved. The dragon agreed to let the student and Pi pass if they could find a way to protect its treasure. So the student decided to solve a problem to find the volume of the dragon's hoard using the disc and washer method. The student knew to use the disc method to find the volume of the dragon's gold hoard. The student knew that the formula needed to find the volume of the pile rotated around the x-axis was volume equals pi times the integral from a to b f of x squared dx. Pi is critical in this equation, which is why the student had to rescue Pi. The student plugged in the x values for a and b and f of x. The volume of the equation v equals pi times the integral from 0 to pi of divided by 2 of cosine x squared dx. When he solved out the integral with his trusty Texas Instrument TI-84 magical calculator, he got 0.785 kilometers cubed of gold.
The student examined the other piles of gold in the dragon's lair, and found the other main pile to be bounded by the formulas y equals the square root of pi and y equals -3x plus 10. The student decided to use the washer method to rotate the graphs about the y-axis to find the volume of the ring of gold. First, he changed both the equations for f of x so that they were functions of y, and he ended up with x equals y squared and x equals y minus 10 over -3. Then he recalled the formula for the washer method, which was volume equals pi times the integral from a to b of long radius squared minus short radius squared dx. Once again, pi played an important role. He determined that x equals y minus 10 over -3 was the long radius, and x equals y squared was the short radius, and that the y values for a and b were 0 and 1.667, and he plugged those values into the equation. The equation he came up with was volume equals pi times the integral from 0 to 1.667 of y minus 10 over -3 squared minus y squared squared dy. When he solved the problem out, he found that the final volume was 44.177 cubic meters of gold. When the student was done, the dragon had more treasure than ever before, and it was so grateful that it let the student pass without trouble. And so calculus returned to the dragon's lair, but it was not enough.
The final test was to face the sorcerer himself. The sorcerer was displeased to see the student, but also intrigued. So when the student demanded that the sorcerer hand over the book of Larson, the sorcerer proposed a deal. He had a riddle for the student, a riddle about a theorem, and the student could have the book if he solved the riddle correctly. The riddle was, if f of b equals f of a, and f of a equals f of b, then what must the slope of f of c be? The student thought for some time and quickly snatched up a stick from the ground. He traced a parabola on the ground, labeled 2 points on either side, a and b, so that their y values were the same. He also traced a third-degree function and a sine function where f of a and f of b were the same. He noticed that in all of these functions, there had to be a point C where the slope was 0. He thought again, because he recalled such a function from his studies. Then he answered, Rolle's theorem.
The sorcerer was furious, but he had made a deal. So he gave the student the Book of Larson, and the student, triumphant, returned to his kingdom with Pi, dispersing calculus as he went. When he arrived home, he was recognized as a hero, even by the algebra and geometry scholars, who had come to realize that calculus was very important indeed. And calculus returned to the kingdom, and it was enough.